Nomenclature of cycloalkanes is relatively straightforward, and it's very similar to the nomenclature of alkanes themselves. The main difference is that the parent name of a hydrocarbon now includes the prefix cyclo to indicate a closed structure. And to illustrate it in an example, this molecule will be called methylcyclopentane. Since we have only one substituent here, a number is not necessary. But in case we have two or more substituents, we need to show their relative positions. So this molecule, for example, would be 1,4-dimethyl cyclohexane. A little bit more complex example could be shown here. This molecule, we can start counting the substituents either from the isopropyl group here or from methyl group here. But if we start counting from isopropyl group, that allows us to give a lower number to the next substituent, which is the methyl group, than in the case where we will start counting at the ethyl group. And so that's why we do start counting from the isopropyl group. And so this is 1, 2, 3, and 4. But once we actually give name to compound, then we still list the groups like we did with alkanes in alphabetical order. So ethyl goes first, 1 isopropyl goes second because ethyl is before isopropyl in the alphabet, and then 2 methyl goes last, and then finally this is a 7-membered ring, so this is the cycloheptane. If in cases that I've shown here, the substituents were smaller than the chain in terms of carbon count. So if we have this molecule, we'll name it as methylcyclopropane. Since our ring has 3 atoms and our linear component has just 1. But if we have molecules which have a long linear part, such as this no name, 1, 2, 3, 4, 5, 6, 7, 8, 9, and a very short, or not short, but small ring, such as this cyclopropane, then this would be 4-cyclopropyl nonane. Meaning that we switch. If we have a large ring and a small linear component, then the linear component is treated as a substituent. Otherwise, if we have a large linear component and a small ring, then the ring is treated as a substituent. Also, if we have 2 rings, the smaller one is treated as a substituent on the bigger one. So this will be cyclobutyl, cyclohexane, and not cyclohexyl cyclobutane. Another thing that is unique about, well, it's not unique, but it's different when comparing cycloalkanes and alkanes, is the fact that rotation around single bonds is free in alkanes, but in cycloalkanes it's not, because closing up a ring prevents the rotation around single bonds, since rotating around the single bond in a ring would lead to twisting of the ring, which at some point becomes prohibitively strained. And so to cut this story short, cycloalkanes have restricted rotation around single bonds. And as you might remember with other case of restricted rotation, which we noticed in molecules with double bonds, restricted rotation leads to isomerism, because 2 things that would normally be related by rotation are now fixed in their structures. And just like we had the case with alkenes, we have an analogous case with cycloalkanes. So if we have a CH3 group one CH3 group on the bottom of the ring and one on top of the ring, this case is a trans 1,2-dimethyl cyclopentane. Or analogously, if we have 2 methyl groups on the same side of the ring, in case it's below the ring, this will be a cis 1,2-dimethyl cyclopentane. And so you see that these stereoisomers is a common theme in different classes of compounds. And so just to remind you, this would be analogous to a cis to butene, in this case to a trans to butene. Now in the next topic we will see what energetic consequences does closure of a ring have on stabilities of these alkenes.